So, but the work was done when he was even in Manchester. Yeah. So, graded dependent model logics. So, I'll start my talk with some brief discussion of the classical results in complexity and decidability of model logics. And with a special emphasis on the distinction and importance between two different problems that we may solve in model logic: local satisfiability and global satisfiability. And later on I will show why global satisfiability is in some modern applications more important than the local one. Next I will pass to the main part of my talk about these graded dependent model logics. I will define syntax and semantics, show some decidability and undecidability results, and some not completely solved problem of classification of these logics with respect to decidability. Then I'll discuss the relationship of these results and this research to the description logic reasoning, which is related to the previous talk. And finally, I will conclude with some remarks and listing open problems. So, the syntax of model logics is very simple. We have propositional formulas, propositional letters, negation, conjunction, and, for instance, one model operator, diamond. And boxes, we can take it as an abbreviation. Here is a definition of the minimal classical model logic, normal model logic K. It has axioms, classical tautologies. It has a special axiom called axiom schema called normality, and two rules, modus ponens and necessitation. And there is a bunch of other model logics, which are typically considered in model logic textbooks. We can add to this minimal system the axioms of reflexivity, symmetry, seriality, transitivity, Euclideanness. Don't bother what do these all terms mean. Well, some are well known, some of course not. Adding these axioms to this model logic K yields some systems. Not all of them are distinct. Here's a diagram of how they are related. Out of 32, there are only 15 model logics between K and S5. And I would like to recall what's the complexity of these logics. So everything in blue is p-space. Everything in blue means that all logics mentioned here, not that all logic between K and C. Yeah. The complexity of what? Yes, and above everything is above K5, everything is NP. The complexity of the problem of local satisfiability. What is the problem? So, assume that we have some class of frames, F. Then we consider the following problem. Given a model formula phi, is it locally satisfiable? Does there exist a model, M, whose frame belongs to this class F? And does there exist a point in this model where this formula is true? Why this problem is typically considered in model logic? The reason is that we have another notion of validity. A formula is valid if it in a class of frames if it is true in every model based on the frames from this class. And a formula is valid if and only if its negation is not locally satisfiable. So we usually investigate the set of theorems of a particular system, or if the system is complete, the set of formulas that are true in all models of this system. And that's why we investigate what's the complexity of this set of formulas. Can we, in which time and space can we decide validity or theoremhood? However, in recent applications, another problem emerged. so-called global satisfiability. Given a model formula phi, can we determine that there exists a model from this class where the formula is true in all points of this model? From the first glance, it isn't clear which of these two problems is easier or harder. And in fact, it can be either easier or harder in some cases. For instance, for logic K, local satisfiability is p-space and the global is x-prime complete. So global is harder. For K4, it is the same in the same complexity class, and for S4, it is even easier. This is a rather simple result, but rather surprising, in fact. So, what if we try to consider the complexity of global satisfiability? The picture is as follows. I didn't find all exact results. So here we have X time complete. Here again P space and P complete for global satisfiability. Here, as I mentioned, S4 is NP complete for global satisfiability. And here I only have an upper bound P space. I haven't found any references in literature where the lower bound was established. Okay, now let's extend our language. Oops, P disappeared here. Sorry. So instead of one diamond, we consider a series of diamonds greater or equal than K for all natural numbers K. These are called graded modalities. Semantics is this formula is true if there is at least a K worlds which are related to a given world W and where the phi is true. So this is an extension of the language of modal logic. And so greater or equal than 1 is the same as just our diamond.
What's the meaning of the existential K?
Existential K. There exists.
No, what does the K mean as a label for the existential quantifier?
It's a natural number, or it's a number of successors where the phi should be true.
Okay.
So, so the usual diamond means there exists a world R related to the given world W, where phi is true. Here we have a more expressive language.
So it says there are K different.
K here and K here is the same K. Fixировано? Да.
It's not a stack of diamonds.
It's a stack. It's an infinite series of diamonds for this. So for every natural number K, we have this modal operator.
So there exists K different future. Oh.
K different successors of a given world where the formula is true.
At least K successors.
Yeah. Of course, since we have negation, we can also express there exists at most K, there exists exactly K, and so on. So the question arises, what's the complexity of these logics for the same classes of frames, transitive frames, reflexive frames, and so on? Well, the picture was obtained quite recently in 2009 by Ian Pratt-Hartman and Evgeny Kazakov. So here we have again P space, here we have again NP, and here, surprisingly, the transitivity gives us another surprise that the complexity of graded modal logics is of transitive graded modal logics is much higher than that of ordinary modal logics. For global satisfiability, for the graded modal logics, the problem of global satisfiability, I didn't find much references, so here is an incomplete picture, which I could either obtain by myself or just find the references in literature. Now, these slides were just introductory, just to warm you up. Now comes the main dish. So, at the beginning we had a language form of modal logic, of unimodal logic. Then we added graded modalities. And now we want to have multimodal. So the question is, what if we have several modalities for several accessibility relations, of which some are transitive and some relations are contained in some order. What will be the complexity of these logics? And the question is not just a theoretical question, it arises naturally from description logic research. Okay, so we extend this language of graded model logics with several. So this was the semantics for the original language. Now we extend it with several modalities. Each is graded. And of course we need to extend the notion of a frame. It will have now several binary relations on a given set of worlds W. Right? Model is defined as in the usual way. We have a frame, and for each propositional variable we assign a subset of W, which is intuitively means that the set of those worlds where this P is true. Now we define, as usually, the notion of truth of a model formula in a given world W of a given model M. The first three clauses are standard, and the last one, you have already saw this with a minor change, so we have a subscript I here and here. Right? And again, a standard notion, a model formula is true in the whole model if it is true in all worlds of that model. So this is a graded multimodal language. Now it's time to explain what is dependent. We want to restrict ourselves, our attention to the classes of frames of a certain kind. The restrictions are of two kinds. Either some relation is transitive, or some relation is included in some other relation. Is a subset. Sorry?
I think it would be useful to get at least one example where more than one successors nature. Why would people consider?
It's the example will be at the very end. It's, for instance, if we model the, if we are talking in our language about the all people, the relationship, so A has child B, so this is a binary relation, and we want to write a policy that if someone has at least 3 children, there is at least 3 are related items which are children, then it is eligible for tax reduction, for instance. Oh, forbidden, yeah. So, to specify these constraints, these classes of frames, we need the notion of an RBox. I use the term that is used in the description logic community. An RBox is a finite collection of assertions of two kinds. Transitivity of some relation Ri, or inclusion. Ri is included in Rj. And we say that a frame with n binary relations obeys these constraints if satisfies this constraint if ith relation is transitive, and satisfies this constraint if ith relations is included into jth relation. So any RBox determines some class of frames. And so by now we have a language. We can build formulas with syntax and semantics. We have classes of frames. So we can formulate a problem. Given a model, fix an RBox. Given a model formula phi, is it globally satisfiable in the class of frames determined by that RBox R? So there is, of course, the corresponding local version, but I'll explain later why we were focused on the global notion only. So if this problem is decidable, then we call this RBox safe. Otherwise, we call it unsafe. So the question is, which RBoxes are safe, which are not? And can we determine this efficiently? RBox is a finite collection of transitivity and inclusion axioms. It's a very finitistic object, and it's natural to ask such a question. Before I proceed to the results we obtained here, I'll introduce a graphical representation of RBoxes. So for instance, if we have RBox of this kind, relation R is transitive, relation S is transitive, Q is a subset of R, Q is a subset of S. We will represent it as a graph with 3 nodes corresponding to the relations Q, R, and S. Transitive nodes will be distinguished by plus, and arrows correspond to the inclusions. Q implies R, Q implies S. So RBoxes are just graphs, oriented graphs with 2 kinds of nodes, with plus and without pluses. So the question is, how can we classify these graphs with respect to their safety? For which graphs the corresponding problem of global satisfiability of formulas is decidable and for which it is not. The first observation is that if we have an RBox which contains 2 separate disjoint RBoxes, then we can deal with them separately. This is due to the results of Frank Walter and his co-authors on fusions of modal logic. In fact, the modal logic with this R is in fact a fusion of modal logic with R1 and R2. And Frank Walter and others showed that whenever we have a decidable logic and some other natural constraints, some normality and so on, then their fusion is also decidable. So we can stick to connected graphs. Okay, good news. Which RBoxes are safe? An RBox is safe if any 2 transitive roles, 2 transitive relations in it are comparable with respect to inclusion. Either R is included in S or S is included in R. So for instance, so one non-transitive role is of course a safe RBox. We can add transitive roles, transitive, non-transitive, something like that. You can notice that all transitive roles are linearly ordered with respect to inclusion. We cannot put plus here because they will be incomparable, which is forbidden by the theorem. And the complexity for one transitive role, if we have an RBox which says transitive R, just one role, one relation, so we have unimodal logic of transitive relation in the graded modal logic, in the graded language, then the problem will be next time. It was on one of the first slides. Now the bad news. Which RBoxes are not safe, for which the problem is not decidable? So here's the first RBox which is not safe. So we have a modal logic with three modalities, say 1, 2, and 3. 2 of them are transitive, the third one is not, and we have 2 inclusions. The third one implies the first and the second. And the language is the graded model language with these 3 modalities. Then the problem of global satisfiability is undecidable, which, so I deciphered this term unsafe. So this RBox is unsafe, which means that that problem is undecidable. We can put transitivity here, and still the logic is undecidable. Flip it upside down. Again, the problem is undecidable. The RBox is unsafe. And the natural question is whether the fourth one is unsafe, is safe or not. It's an open problem by now. So the problem is we have a model logic with three modalities. All of them are transitive, and we have two inclusions like this. Whether for this logic the problem of global satisfiability decidable or not. In fact, for this particular RBox, the problem of global satisfiability and local satisfiability are decidable or undecidable simultaneously, because we have this transitive super role of all roles in our super relation of all relations in our language. And that's not the end. We also have chains like this. So notice the ends of chains are always transitive and intermediate nodes are not transitive, and we have interleaving direction of implications between them. So this is an infinite series of RBoxes which are not safe. So now the question is, what is in between? On the previous slide we saw some safe RBoxes. Here we have a series of unsafe RBoxes. Are there any others? We introduced the notion of so-called semantic conservative extension. So we have one graph and another graph, and we want to know, let's say that the other one contains the first graph. We introduce the notion of semantic conservative extension. R prime is a semantic conservative extension if any frame that satisfies the first RBox can be extended by interpreting the relations that do not occur in R to the frame that satisfies R prime. Let me illustrate this definition. On the left we have an RBox with three relations, R, V, and S. Two of them are transitive, V is not. And on the right we have, again, it contains this one and additionally contains another relation. Why? This is a conservative extension of that. So if we have a set W and three binary relations on that obey this RBox, can we insert a transitive relation in here in order to satisfy this RBox? Of course, we can take just intersection of two transitive relations. It is intersection of two transitive relations is again transitive, and it will be a super relation of this relation V. So any frame satisfying here can be extended to any to a frame satisfying this RBox. However, if we flip this picture upside down, then the question is no. If you can easily build two transitive rows on some set W, which are transitive, but their union is not transitive, and take V to be their union, then you cannot insert a transitive relation that is in between R and S and V. Therefore, not every frame satisfying this can be extended to a frame satisfying this. Right? From the definition, it is not clear how can we check effectively that one RBox is in a conservative extension of another one. Yeah. Consider some set W and three relations. Of course, you know that the union of two transitive relations is not always transitive. Consider such a counterexample, then take R and S to be those transitive relations, and V to be the union of them. Then you cannot insert another relation in between them so that it is transitive.
Okay, thank you.
And Evgeny Kazakov showed that this relation can be checked in polynomial time. The proof is not quite straightforward, but It's not very hard. And why this notion is useful? This theorem justifies that it is really a useful notion. If R prime is safe, and we have R as a so R prime is a conservative extension of another RBox R, then R is also safe. So this relation is a true easier than relation. So we have one RBox, we have another which is conservative extension. If this one is simple, then is hard, then that one is at least as hard as this one. And it is just a graph theoretic theorem. For any connected RBox, so for any connected graph of that form, with these two kinds of nodes, it is true that it either has all transitive relations comparable with respect to inclusion, and so this RBox is safe by the first theorem, or it contains, in the sense of conservative extension, one of those RBoxes that I've mentioned on the previous slide, including, so these are repeated here again, including this red one for which the problem is open. So we have a borderline. Below we have all RBoxes which are safe. Any two transitive relations in them are comparable with respect to inclusion. And above this borderline we have, so these all RBoxes are minimal in a sense. They do not have any part in the sense of conservative extension which is unsafe. So to complete the classification, we only need to solve this problem.
And there's infinitely many.
Sorry?
Infinitely many.
Yeah, infinitely many for
Minimal.
infinitely.
The number of minimal unsafe blocks is infinite.
Infinite, yeah. It's an infinite series of graphs. So if we show that this RBox is also unsafe, then the classification is complete. However, we believe that it is safe. So we suspect that the classification is not so easy. Now the relationship to description logics. So as was told in the previous talk, description logic is a family of decidable logics which are used in knowledge representation and reasoning. And it appeared that they are related to multimodal logics, although it was noticed not at the very beginning of the research on description logics. And they have reinvented some results, some decidability and complexity and efficient algorithms and so on. These logics use some fancy symbols for conjunction, disjunction. And there are prominent systems realized which implement the reasoning algorithms for these logics. For those who didn't encounter description logics before, just very recently, just 2 weeks ago, a paper called Description Logic Primer appeared on archive.org. It's a paper for those who have never heard of description logics, just to introduce you to this area, what's it all about and how it's all related to our reasoning. There is a handbook of description logic, and there is a resource, a web page on the web, just Google for it, for this title, which shows, well, there is a huge family of description logics, and for many of them, the researchers have found whether they are decidable or not. Most of them are decidable, and which is exact complexity of each logic. And all these results and references and some explanations, these are collected on this web page. Here is a syntax for one of the description logics called ALCQ. And as you might notice, it is just a notational variant of a model of graded modal logic, graded multimodal logic we saw before. So we have atomic concepts which correspond to propositional variables. We have negation and conjunction. And we have graded modalities written in different notation in that logic. And in fact, this is not just a coincidence. The semantics of the first and the second syntactic objects are just the same. So this is really a notational variant. This graded modal logic is a notational variant of this description logic. They have a notion of a terminology, which is a finite collection of axioms of this form. One concept is included in another. But using this correspondence, we can build a model formula. We can build a model formula that corresponds to C and D, and take a conjunction of them. And so we will have any T box will be transformed into a model formula in our language. And the most important problem in description logic is, given a terminology, whether it is consistent. Many problems that arise in description logic are reducible to this problem of consistency of a terminology. And in our terms, consistency is the same as global satisfiability. That is why global satisfiability of a model formula makes importance in this area. And there is also a notion of an RBox in description logic. Originally came from description logic. An RBox is a finite collection of axioms of two kinds, transitivity and inclusion, which is exactly what we had in our logics. So, and ontology is a pair of a terminology and an RBox. And the main problem here is, again, given a terminology T and an RBox R, whether it is consistent. And in our terms, we can just rephrase it using this translation. We can rephrase it in our terms. Consistency of an ontology is the same as the global satisfiability of phi with respect to this RBox. And it was noticed quite earlier that if we combine this logic LCQ, shown on the previous slide, with RBoxes, this logic is called SHQ, it yields to undecidability. However, in the original proof of Haurock, Sattler, and Tobias, there were 8 relations. 4 of them are transitive, and 4 are not, and some inclusions between them. So we have strengthened their results to the case of 3 modalities. And what is the remedy that the description logic community takes? In order to avoid undecidability, they simply forbid transitive roles in these expressions. Transitive roles and roles that contain a transitive subrole. So our claim is that for many practically, perhaps hopefully practically useful RBoxes, the problem is still decidable. So this is the first theorem on safe RBoxes. So here's an example of an RBox. So we have a relation has a relative, has descendant, both are transitive, has child, has son, has daughter. So this is an RBox, and this is a safe RBox. All transitive roles are comparable. So if you have only these relations and these RBox in your ontology, you can use these relations in number restrictions, in graded modalities, and still have a decidable logic. However, the reasoning algorithm, of course, will be different. So the question is, in real ontologies, which we have in practice, are the RBoxes safe or not? It's natural to just inspect those ontologies. We didn't do this so far because the ontologies are quite huge, and RBoxes are huge as well. So we need some technical instruments for doing this. So the conclusion, we have found a large family of decidable logics, logic with safe RBoxes. So we say that you can use transitive relations in graded modalities or in number restrictions and still have a decidable logic. And found a large family of unsafe RBoxes. So we suggest just to check, if you have an ontology, check whether it has a safe or unsafe RBox. And then if it has a safe RBox, then you can freely use number restrictions. But we need, of course, another reasoner for these logics. I didn't mention in these slides, but if we enrich our language with inverse modalities, then the effect is disastrous. We easily obtain undecidability even for one transitive modality.
What does it mean inverse?
So graded modalities mean there exist at least k successors where phi is true. Inverse modalities mean there exist at least k predecessors where phi is true. So there exist at least 3 children which are doctors, or there exist at most 2 parents which are something. So it's a inverse relation. So if we consider a graded inverse model logic with one modality over the class of transitive frames, it is undecidable. It's just a very recent result. And here a minor point is that if we allow to count over successors, but do not allow counting over predecessors, or only saying there exists a predecessor for all predecessors, but not counting at least 3, at most 5, will the logic be decidable? And this is practically useful because in many applications we need to count successors but not predecessors. We need to consider, for instance, genes which contain at least 3 proteins of a certain kind, but we don't need to consider proteins which are contained in at most 5 genes of a certain kind. It's quite ridiculous. Well, anyway, the question is meaningful both theoretically and practically. And what's left? So what is left is already mentioned on the slides, whether the red RBox is safe or not. Does the uniform decidability holds? So we fixed an RBox and asked the question whether the problem of global satisfiability of formulas with respect to this particular RBox is safe or not. If we consider a combined problem, given an RBox and the formula phi altogether, can we decide whether phi is globally satisfiable with respect to R? It's a different problem. The problems of this kind were not considered in model logic, to the best of my knowledge. Well, all my talk was about decidability. So what's the complexity of the decidable logics we've pointed? Well, the same questions for local satisfiability, but this is just more theoretically interesting than practically, and practical algorithms. That's it for me. Thank you.